Francis, can you hear me okay?
Yeah, I can hear you.
I couldn't hear you. I saw you unmute, but I couldn't hear you.
Dear. Can you hear me now or no? No, okay.
Francis, I can't hear you. Is that some problem with my volume? Maybe that is. Let's see. Can you say something again? I think I had my volume down.
Can you hear me or no?
Yes, I can. Good. All right, good. There. Wow. Look at you. You've got a friend with you, Francis. That's nice. I may. That's great. Far out. I'm used to seeing a lot of cats. The first bird I've seen in a while. It's nice. Just waiting for other folks to get here. I may take a quick run downstairs just to make sure there's no one down there. Back in a sec. All right, well, we seem to be missing a few people today. I'm not totally sure where they are. But it's just the four of us here. They're not downstairs. So great if you guys can leave your cameras on if you're willing to. Makes it a little bit easier to have a conversation. I can see people. Has anyone heard from any of their partners and in this class? I'm just wondering where people are.
I had class with Ari this morning and they said, see you at 1. So I'm sure that they're on their way or going to be here soon.
Okay, well, here's Sadie. How are you? Like Justin's enjoying himself on the beach someplace.
Sorry for being late. The line for food was really, really long.
All right, well, we are still missing a good portion of the class, but I did just run downstairs and check, and there's no one down there. So, I think maybe we will go ahead and get started. Let me share my screen. And I'll share my screen. Let's see. Go into presentation mode here. All right, can everyone see my screen okay? Okay, wonderful. So haven't had a remote class like this for a while, but definitely seems like a lot of people on campus are either getting COVID or have been exposed to COVID in the last few days. So I had the smallest 101 class I've ever taught this morning. Well, lots of people on Zoom, but small in person. So thought I would go ahead and do this. So we're kind of at a shifting point in the semester in terms of what we're going to be covering in class. So goal up to this point has been essentially to give you this set of basic formulations, get you to a point where you could start, building a model that would be interesting and that would manifest some issues that you're interested in examining and allow us to look at those. And so for a good portion of the remaining classes, we're going to be looking at not having you build models so much anymore, although we will still build a few models together, but kind of looking at modeling application. So that's where we're kind of shifting at this point, is more of a focus on looking at what you can do with models, beyond kind of the exercises that you've done.
4 people.
Where
7. Oh, sorry.
Avi, you're not muted. Yeah. Beyond kind of, understanding that developing your understanding of these underlying formulations, really applying those to particular situations. And so the model I want to talk about for a good part of today is a model of a real thing. And that is, hopefully does anyone recognize that building in the bottom right hand here? What is that building?
That's the research facility for environmental studies.
Yeah, AKA the HLC Annex. So that was an old building that was kind of, we sort of made a decision a bunch of years ago. I'm not really sure if we made the right decision, but the decision was, should we tear down that house and build a lab, or should we do an adaptive reuse of that house and kind of demonstrate principles of adaptive reuse of a facility? And we decided to do the adaptive reuse. So on the left-hand side, you're seeing what that house looked like when we started the project, which was pretty derelict. And then you're kind of looking at it when it was finished on the right. One of the decisions, and we had a bunch of students involved in this design process, one of the decisions that we made was to convert what had been a porch, or most of what had been a porch, into a sunroom. And so one of the things we're going to look at today is, okay, let's examine the issue of sunrooms and their environmental benefits and what they can contribute to a space. And so we're going to play around today with a model that is based on some very simple first modeling principles, basic formulations, specifically based largely on the gradient equation. and look at, how does that play out if you're really trying to examine how a real structure is operating and you actually want to be able to apply that model to making management decisions. So I want to give you that sense of, we've been dealing with these kind of simplified models that utilize basic formulations. How does that work if we want to sort of play that out and really look at a real live situation and apply modeling? So that's kind of the goal of today into this next exercise, is to take a look at how that would work. So before I get going on that, hey, if you guys don't mind and you got the bandwidth, would love to see your faces, those who've joined the meeting, so that I'm actually looking not at black boxes, but at people. So if you're up for it, appreciate that. But I want to talk about a couple sort of details before we get into that. One is that you do have a quiz, as it says on the syllabus for this weekend. So that's the easiest way to assign that is to make that something that you do with your modeling partners. So that's a thing. It will cover all of the material we've done up until the semester. It won't be that dissimilar from the previous one, but we've covered some new formulations and stuff since then. You guys have now turned in your modeling proposals. There's a modeling critique. I'll say a little bit more about that in a minute. And then I'm gonna, like I say, spend the bulk of today talking about, an application of some of the principles we've been learning to a real life modeling situation. So let me just say a little bit more about kind of where we are in the project time frame, just because that's also going to be an important component. But the two things we're really going to focus on for the remainder of the semester is modeling applications and getting you guys up and going and making progress on the modeling projects you're developing. So the next assignment related to these projects is a critique of other people's proposals. And I will shortly assign you to proposals to review. We're still doing a little bit of adjustment here in project groups. Yeah, I don't want to assign the critiques quite yet, but this is sort of where we're going moving forward. Later part of no, I guess that's Tuesday. We've got our modeling. What is the 26th, Tuesday or Thursday? Help me out here. The 21st.
I think it's Tuesday.
Yeah, it's Tuesday, right? So on Tuesday, you will have critiqued other people's proposals, and we will have a project conference where we'll get to sort of I'll sort of circle around with each group, and we'll try to really dig into getting you guys started on your models. And then the next due date will be your final project proposal revised, so sort of revised based on the feedback you get. And then, as you see, we've got several labs built in the rest of the semester. We'll basically be spending the class focused on helping you guys move forward on your modeling projects, and then a final presentation and written project report. So that's kind of where we're headed in terms of the modeling projects going forward. Any questions on modeling projects before I go into today's topic? All right. So the topic today is sunrooms, but the issue really has to do with the larger one and buildings and their impact on the environment. If you care about, oops, now I'm not showing up on video. Oh, it does that. If you care about the environment, you should really care about what goes on within buildings. About a third of the total energy used in the United States is used to support activities that take place in the built environment. About 2/3 currently of the electricity used in the United States is used for operating or activities that take place in buildings. About a third of the CO2 emissions in the United States are attributable to activities in buildings. And this statistic is a little bit out of date. It shifted a little bit now, but 5 or 6 years ago, about 9% of global CO2 emissions were attributable to activities that took place in buildings in the United States. So buildings account for a substantial fraction of resource use, 12% of freshwater resource as well. And a lot of that energy that's used in buildings is actually used for heating and cooling in buildings. And so the issue of how we heat and cool our buildings is actually really important to thinking about how we solve issues of climate change. So that's something that's important to kind of think about. It turns out that on the Oberlin College campus, buildings are also, the principal source of resource consumption within campus. And so, how we go about heating and cooling our buildings, and obviously this enormous sustainable infrastructure project, the so-called SIP project taking place right now at Oberlin, is focused very much on how do we reduce the environmental impact of buildings? How do we transition from buildings that are essentially using a lot of fossil fuels to operate to buildings that are running on renewable energy, ultimately running on solar energy. So the topic of today, though, is to focus pretty explicitly not on heating and cooling buildings through geothermal systems or something like that, but how can we use sunlight directly to heat buildings? And so the overall learning objectives for this particular model are to give you guys experience with models, again, as practical design tools, not just things that can be used in a very sort of general sense to model our general understanding of relationships, but to get specific about that. I also want to give you a sense of how knowledge of a particular field, passive solar architecture, combined with a knowledge of modeling, can be used to develop models that actually are useful to us. And I also want to use this as an example of how we often do something called parameterizing or parameterization in model simplification. And I'll get into that a little bit more. But as on the first day of this course, we talked about models as a simplified, abstract representation of reality. Even when we're building simulation models, we're often looking to take complicate things that are complicated to model and make them simpler to model. And so we're going to talk a little bit about some of the simplifying assumptions that go into solar architecture to make it easier to design buildings that operate on sunlight. So that's kind of where the parameterization comes in. So if we want to get specific in terms of the questions that we're going to be addressing, we're going to consider what factors govern thermal performance of a sunroom in particular. So a portion of a building that is explicitly designed to capture solar energy. And then given architectural and climate constraints, how might we design a sunroom in Northeast Ohio to manage it to maintain a specific temperature range? So if we're trying to maintain a temperature, in this case, between 40 and 90 degrees Fahrenheit without using any auxiliary heat source, what kind of decisions can we make about how we design the sunroom, how we manage the sunroom to accomplish that goals? And then what are the implications of different design and management choices? Things like window size, window material, heat storage. If you are thinking about a supplementary heating system, all of those sorts of things. And so what we're going to do is we're going to build. This will be your last actually modeling assignment, other than your modeling project. But we're going to build the kernel of a much more complicated model so that you basically understand everything that goes into making this model work, but then we're going to explore a fully developed model. So when you look at the fully developed model, and we'll do a little bit of a tour of that model today, it's going to look complicated. But by building the kernel, I want to give you the sense, yeah, it's a little bit complicated when you're actually trying to make a model behave like a real structure. But actually, the underlying assumptions and everything else are pretty darn simple. They're not that complicated, and they are based on things that at this point in the class you understand well. And so I want to give you the sense that even though the final model we'll look at may look complicated, it's actually something that you could build. You could build right now with the skills you've already developed in this class. So first, I want to say some general things about, sunrooms and as objects. Let me just do a quick go around here. What are people's experiences with sunrooms in the class? I'm going to ask everyone to answer that question. How have you experienced sunrooms? What has been your experience in sunrooms? I'll start with you, Francis, if you don't mind.
Yeah, they get pretty warm, like no matter what season it is. As long as your windows are sealed properly, they get pretty warm, even if it's in the winter. So it's kind of nice, but it can also get really hot in the summer.
Sure.
So it's good to have blinds and stuff.
Okay, cool. Who wants to go next? Or popcorn? How about we do it that way?
Okay, Sadie, do you want to go?
Yeah, very similar experience. I've only ever been in one, but it was really humid. Really humid and actually very nice to kind of just like sit there and enjoy the sun. But yeah. Popcorn Shantini.
Yeah, my grandparents have a sunroom. There's like a lot of like vines growing on it. My grandmother uses it as like a little greenhouse. So there's like growth during the winter indoors. Yeah, popcorn to Ari.
Okay, I was gonna say something similar, not with my grandparents, but my really good friend from home also has a sunroom where it was like had a lot of plants growing there. So that's kind of my only experience with that. And also, yeah, I guess just what everyone else said. It's really warm, which is really nice in the winter. I'll pass to Justin.
I haven't had that many experiences with sunrooms in Virginia. I feel like it's pretty warm. So, but it looks nice. I'm gonna pass it to Avi.
I had a friend in high school who lived really close to school, and we would go to his house after and hang out in his sunroom. But I don't think it was facing the right direction because in the winter it was still really cold in the sunroom because I don't think the sun was at the right angle. I'm gonna popcorn to Mads.
Sunrooms, I'm similar to Justin, like in Texas, sunrooms aren't really a big thing because they get so warm and it would not be a good place to be in the summer, but they seem really lovely.
All right, have we made it through everyone here? I think we have. So people have had different experiences with sunrooms. I heard some people say tend to be warm, sometimes too hot, sometimes moist. I heard a comment about sunrooms, experiencing sunrooms that weren't necessarily pointing in the right direction. And in fact, for a lot of people who purchase sunrooms, they are kind of aesthetic features. It's like, oh, that would be nice to have this sort of windowed space, give me the sense of being outside. And there's actually a sunroom a little bit west of me on Prospect Street that I always am amused by because it is facing north, which is exactly the wrong direction to situate your sunroom. But hey, they made aesthetic choices. From a solar gain standpoint, that's a pretty terrible place to put a sunroom on the north end of the building. But these things are done. Some people use them for growing stuff, heard about the vines. From a solar architecture perspective, a well-designed sunroom can be used to actually acquire extra heat for a building. So they often have a great potential value, but the way they're installed, oftentimes are compromises and are not necessarily achieving solar performance. If you are interested in solar performance, that is really trying to maximize the extent to which you're accepting heat when you actually want heat, minimizing heat gain when you don't want heat, and storing that heat, then you need to actually give quite a bit of thought to how it's designed. And again, the key goals from a solar architecture standpoint is heat gain. That is trying to maximize the amount of heat you're getting when it's desirable and minimize heat gain when it's not desirable, heat loss, trying to maximize when desirable and minimize when undesirable. And then heat storage, which is something that none of you mentioned, but is a potential for what one can do if a sunroom is well designed. And it's kind of a key aspect of both the kernel model that you'll develop and the model the sort of more developed model that will be shared with you. One key distinction when we're talking about solar energy in houses in general, and sunrooms in particular, is active versus passive solar design. An active solar design is one in which that heat gain is managed with a mechanical system of some sort. So when heat comes into the space, that heat is moved around through some sort of mechanical system to store it, and then delivered through some sort of mechanical system as well. Whereas in passive, there's no use of any kind of mechanical system to distribute that heat. Okay, so I need to give you like a bit of background on basic heat flow and different kinds of heat flow in order for you to understand some of the factors that you need to think about in designing a sun space. One kind of heat flow is radiation. Radiation, as you guys probably understand, is energy transmitted as electromagnetic waves. So, the sunlight traveling from the light traveling from the sun to the earth is radiation. It travels in the visible spectrum, it travels in the infrared spectrum, travels in the ultraviolet spectrum, but it's all sort of different wavelengths of light that are moving towards us. Radiation is unusual as a kind of heat transfer in that it can travel through space, it can travel through a vacuum, it can travel through windows. So it can travel through a lot of media that other things cannot travel through. When radiation is absorbed, it's converted to heat. So a surface, and different surfaces absorb heat differently. As you guys are well aware, a black surface absorbs lots of heat. So a black surface is going to maximize that absorption of radiation and conversion of that radiation directly into heat energy. Radiation can also be emitted from hot surfaces. So when something heats up, it is emitting radiation. And you experience that if you're in front of a fireplace, part of what you're experiencing as warmth is convection, the direct movement of heat from the fireplace to you. But part of it is that it is emitting infrared heat, and your body's absorbing infrared heat. Probably a better example of that is when you're outside on a day in which the air temperature is cold, but it's very sunny, and your skin actually feels warm, even though the outside temperature is cold. And that's because your skin is directly absorbing that light energy, especially a cool day that is relatively still, there's low wind, with good sunlight, your skin will be absorbing that radiation from the sun, directly turning it into heat. So your skin temperature is actually warmer than the air temperature, and you feel comfortable, even though it's actually cold around you, and it's because you're absorbing that radiation. Of course, the sun goes behind a cloud, and then you suddenly feel cold again because you're no longer absorbing that. So as I mentioned, color is important. Black objects are good at both absorbing light energy, light radiation, and converting into heat. But black objects are also very good at emitting heat radiation, infrared radiation. So color's important. And in a general sense, when you're building a structure that you hope to be to exhibit, desirable solar performance characteristics, you can exhibit control over various aspects of radiation. You can put shades on windows, as was discussed when people were giving their experiences with sunrooms. Shades are important if you've got a lot of solar radiation coming in through the windows. And it's getting too hot in there. Shades can control that flow of radiation. It can block or reflect that radiation. And those shades can be equally important at night. If you pull shades at night, it prevents the room from radiating heat through the window out into the cold outdoors. So simply pulling down a shade at night is a way of blocking radiative escape out from your inner space to the outer space. And so you can keep a space warmer inside. So anyways, radiation is one really important kind of heat energy, way of transferring heat. Another is conduction. So conduction is heat flow between two materials that are in contact with each other. And, as we briefly talked about in this class, and as you guys have no doubt talked about in other classes, one way of expressing the second law of thermodynamics is that heat spontaneously flows from hot to cold. So if you have objects of different temperature in contact with each other, heat will flow from the hotter object to the cooler object and try to sort of equalize that temperature difference. And again, as with radiation, there are various ways we can intervene in the system to control that flow of heat, to try to minimize the heat flow, or in some cases to maximize the heat flow. But we've already talked about insulation, for instance, as something that slows down the conduction of heat, or conversely, the other way we talked about it is increases the resistance to heat flow. And again, that's where that R factor comes from on insulation, because the R factor is telling you how much that particular insulation is slowing down the conduction of heat energy from one side of that insulated material to the other side of that insulated material. The bigger the R value, the more it blocks conduction of heat flow from one side of whatever the insulated object is, a wall, for instance, to the other side of that object. So controlling that is super important. And then finally, there's one more important kind of heat energy, heat flow that we need to consider when we're thinking about solar design, solar architecture, sunrooms, and that is convection. So convection is the physical movement and mixing of heat that is contained in a gas or a fluid. So conduction is it just sort of moving through an object, conducting through an object, whereas convection is you're actually taking a warm mass of air or water or something else and moving it from one place to another place. And there are some principles. Warm stuff tends to rise, and so you can take advantage of that in the design of things and design things so that you naturally cause air to move around and cycle in various ways, based on the fact that warm material tends to rise. Anyway, those are kind of some basic principles that you need to be thinking about when you're thinking about, solar architecture. Any questions on anything I've said so far? All right, so heat storage. This is another really important thing to think about if you're trying to design a solar space, because this at some level, this is like one of the great challenges of operating the world on renewable energy. Not just heat storage, it's energy storage in general. The sun, secondary solar forms of energy like wind, they're variable. Sometimes they're there, sometimes they're not there. And if you want to run a human system, a human society off of wind and sun and tides and other things that are intermittent in their availability, then the question of how you store that energy is just absolutely critical. And that's, in solar architecture, the thing you're trying to store is usually heat. So heat storage is really important. And when we talk about heat storage, we talk about it in terms of, we use various terms, one of the key terms being thermal mass. So the thermal mass of something, it's like if you think about how heavy something is, and weight is sometimes related to thermal mass, but it's a different concept. It's kind of an analog of weight. The thermal mass of something is like how much material can absorb, store, and release heat. So something that has a high thermal mass is something that's good at storing and releasing heat. So thermal mass becomes a really important component of designing solar systems. And it's a function of the volume of the object, the density, the specific heat capacity, the thermal conductivity, the surface color, and its thickness. All of those things come into play when you talk about thermal mass in a solar heat storage system. And different materials have very different thermal mass. So water has a great deal of thermal mass per volume. So it has, and by the way, you're going to notice that today I'm using, I'm not using any metric units. I'm using English units. And I will say that this, the model that we're going to work with in this is a model that I built with a colleague who's a solar architect. I met him at a conference, and we decided to work on this project together, and got some NSF funding actually to build the model that you'll ultimately be working with. But I originally, I wanted to, being a natural scientist and wanting to do the right thing, I wanted to do all the modeling in metric units, which, is what we're supposed to use in the sciences. And he said, can't do that because solar architecture in the United States is all done with English units, and it just won't work if you try to do it in metric units. And it didn't take very long for this guy to basically convince me that we needed to use English units, because that's the way all of the data out there exists, and all of the sort of equations and everything else that are used in the United States, they're all using English units. So anyway, you'll notice that I'm using English units here instead of metric units. Anyway, so water has this density of 62 pounds per foot. Its heat capacity is 1 BTU per pound per degree Fahrenheit. So that's a measure of how much energy it can store, 1 BTU per pound per Fahrenheit. It's kind of the definition of a BTU, actually. That's why it works out cleanly that way. Whereas air density, it's very, very low density air. Obviously, it's floating in the space around us. If there was water in the air, it would sink to the bottom. Its heat capacity is very low. So point being, the key point to take home here is you can store a lot of heat in a little bit of water, and that same heat in air, air stores a lot less heat. And by the way, just to make this a little bit more concrete, that is why temperature fluctuates so darn much in a desert where the moisture is really low, because it doesn't take a lot of energy to heat up that air, and it doesn't take a lot for that air to lose its heat. That's actually part of the reason why living in close proximity to a large body of water like Lake Erie, or if we were living on the east coast or the west coast, those large bodies of water next to land masses temper heat fluctuation. Spring arrives later, summer ends later when you're near a large body of water, because that large body of water is capable of storing. It has so much thermal mass, it can store heat, and then it can release that heat. So it dampens the fluctuation of heat. We obviously have much less fluctuations in heat in Northeast Ohio. I mean, we do have fluctuations because of convection, that is weather masses moving through. But on an annual basis, we have much lower fluctuation in heat here than we would if we lived further west of here, past the Great Lakes, where there's not large bodies of water that are tempering variability in heat. So that thermal mass of Lake Erie and any other large body of water really dampens fluctuation. And that's a really important principle to think about in solar design. If you're trying to build a house or a sunroom that's comfortable over long periods of time, building in a lot of thermal mass to dampen that heat fluctuation turns out to be really critical to maintain that. And thermal mass you can think of as sort of like, sometimes it's embodied in a hard object like walls, cement walls, bricks, mortar. They possess a lot of thermal mass, but you can also potentially store a lot of heat in water, and then you can actually potentially move that water around within a space and modulate temperature variability that way. So you can control and dampen thermal mass in various ways. Now there's a very, very important concept that solar architects use, one that was introduced to me when I sort of began collaborating with the solar architect, which is called the diurnal heat capacity, or DHC. It's basically every room, every building will have a diurnal heat capacity. It's the amount of heat energy required to raise the internal temperature of a room 1 degree Fahrenheit. So if there's a lot of thermal mass in that room, it will take more energy to heat or cool that room than if there's very little thermal mass within that room. So it's kind of a function of, what kind of materials, how thick those materials are in the walls, the ceiling, the floor, and also in objects in a room. Depending on how you have a room furnished, it will have a different diurnal heat capacity. And one of the kind of rules of thumb of solar architecture is when you have a wall or a floor that has some thickness to it, beyond 6 inches, whatever is beyond that 6 inches really doesn't matter, because of the rate of conduction, it's too disconnected from the room to affect its diurnal heat capacity. So having a super thick concrete wall around you, the first 6 inches are going to matter of that concrete. Beyond that, it's basically too far away from the room to have an impact. So diurnal heat capacity, DHC, important concept I was introduced to. So when we think about changes in temperature, a change in temperature is a result of a heat flow divided by the diurnal heat capacity of a room. So how fast, how much temperature change there's going to be is a function of how quickly that's flowing divided by the diurnal heat capacity. The more diurnal heat capacity, the less the fluctuation in temperature is going to be in a room. And if that looks a little bit like a gradient equation, it makes sense, because almost everything associated with solar architecture looks like a gradient equation, because almost all of them are variants of a gradient equation. So like I say, you learn these sort of simple principles and they play out. And if you're interested in going on in solar architecture, it's all about gradient equations. If you're interested in going on in hydrogeology, being a hydrologist, it's all about gradient equations. It's just, if you're interested in solar architecture, you're talking about radiation being absorbed, being stored, flowing through various different media. If you're interested in hydrology, you're interested in water moving through semi-porous media, but it's actually pretty much the same thing, just a different context. Okay, well, you guys, we talked a little bit about windows before. I mentioned that the AGLC, when it was built anyway, was very unusual in having these triple paned windows, which is what's diagrammed here in the middle. And that the point of creating a triple pane window is to create two thermally isolated or yeah, 2 isolated air pockets. Actually, as I mentioned, oftentimes they're filled with argon gas, which is actually labeled here because it's got better insulation value than air or nitrogen in our air. It's mostly what our air is. And then I have a bunch of materials here, and they're kind of labeled with their R value per inch. So you know, plywood actually conducts heat pretty well, so it has a low insulation value. Heat can move through, can conduct through wood pretty well. Glass fiber, cellulose, polystyrene. You're just looking at different materials here, and this is just comparing per inch how resistant they are to heat flow. And you know, we've talked about this before. Thermal resistance R is the resistance of that material to heat flow through it. And as I pointed out before, you know, in some contexts, when we're talking about gradient equations, we use resistance to the flow of something, and in some contexts we use conductivity. And the weird thing about the building industry is they use both of these terms. When they talk about walls, they use R factors, but when they talk about windows, they use a U factor, which is conductivity. So it's 1 over R. So same field, but they're using both resistance and conductivity in one field. They use conductivity when they talk about windows, and they use resistance when they talk about walls. Go figure. Don't know why it's done that way, but just these things evolve as they do, and then people keep doing them the same way. But now sometimes you can add additional materials to windows in particular, but also actually sometimes to walls. You can coat those windows in ways that doesn't necessarily change their conductivity to heat, but changes how radiation interacts with them. So you can tint windows in various ways that will affect how the particular wavelengths of light travel through them. And one thing you'll very often hear, you know, solar architects talking about when they talk about windows is low E coating. And low E coatings are used to selectively block infrared radiation from flowing through the window. So you don't necessarily see a low E coating, but low E coatings can be put on windows to prevent either infrared radiation from getting in through the window or infrared radiation from flowing out through the window. So you may want light coming in through the window, but you may want to block heat. Like if you were living in a southern climate, you might really want to be getting light in through your windows, but you might really want to not be getting the infrared portion of the electromagnetic spectrum in through your window, because all it's doing is adding to your heat load and making you spend more energy on air conditioning. So anyways, all kinds of coatings you can put on windows to try to affect the way various radiations interact with that window. So it turns out all of these things are, there's some real sophistication to designing these things. As a matter of fact, I just went on a tour of the you know, the sustainable infrastructure project at Oberlin 2 days ago, and was, you know, I mean, you guys have obviously probably looked in these trenches that have these big pipes in them. Those pipes are going to be circulating water. They're using, this is, it's not really a solar system. It's going to be a ground source heat pump / geothermal system. But many of the principles we're talking about today are like absolutely central to what they're doing in the SIP project. And I didn't quite understand how they were doing this, but they've got I'm forgetting the name of this particular insulation material, but in these trenches that they've dug and laid the pipes, they're basically filling them with this kind of dense insulation material that's a good insulating material before then they put dirt back on top of them. So they're going to be sort of embedded in this. The pipes themselves are not insulated, but they're going to be embedded in this insulating material that has what kind of an R value? What are you looking for in an R value of that insulation? High or low? Do they want a material that has a high or low R value in that, buried in that trench?
Be high.
Absolutely. They're trying to get the highest possible R value so that they minimize heat loss as they're going to pump water. The way all the dorms and other buildings on this campus are going to be heated is there'll be hot water generated in the plant through a heat pump system connected with a bunch of wells that go deep into the ground. They'll be creating hot water, pushing it out through all those pipes to all the campus buildings. And then in those campus buildings, they'll have radiators that are designed to radiate that hot water into spaces. And then the cooler water will flow back. And they want as little as possible heat loss between the central heating plant and the buildings that it's being delivered to. And a high R value of insulation in the trenches is what's going to minimize heat loss and allow us to use the least possible energy to heat this campus. Any questions so far? All right. Okay, so let's talk about like heat gain and loss in buildings. One important way we gain heat in buildings is through solar gain through windows. So you've got windows and they let light through. That light is absorbed by surfaces within the building, and then that's turned into heat energy within the building once it's absorbed. Another important gain and loss is through conductive and radiation losses through windows and walls. So your walls, heat is being conducted through the walls, it's being conducted through the windows. And as it gets, the colder it is outside, the bigger the gradient, the difference between the inside temperature and the outside temperature, the stronger the force trying to cause that heat to flow from inside the house to outside the house, or from outside the house to inside the house, depending on whether it's summer or winter, and whether it's, whether you're trying to maintain a cooler space inside the building or a warmer space inside the building. Also, equipment and animals within buildings are generating heat. So anything that is an electric appliance in a building is taking electricity from the wires, and at the end of the day, it's turning all of it into heat inside the building. So if that electricity is being used to create lights, all that lighting is eventually turned into heat within the building. If it's being used to run your computer, if you put your hand on your computer is warm. Basically, your computer is a little heater turning electricity. Everything that accepts electricity is basically turning it into heat. Even your air conditioner, even not your air conditioner, even your refrigerator, you think of a refrigerator as an object that cools the air inside of it, or a freezer that puts air below 0 degrees in it. But actually, that refrigerator is heating your space because it's cooling the inside of the refrigerator, but it's actually just pumping the heat from inside the refrigerator into the coils in the back of that refrigerator, and that heat is being dissipated into the space. So as an object, a refrigerator is actually a heater. Takes electricity and turns it all into heat energy, which is all emitted back into your room. By the way, that's why it's not a good idea to open the door of your refrigerator and stand in front of it on a hot day to cool yourself down, because all of that coolness being delivered to you on that side of the refrigerator is being delivered to the coils on the back as heat energy and more. So you're actually heating up your room by opening the refrigerator door. It seems like you're cooling the room, but you're not. You're heating up the room by opening the door. Anyway, you've got all this equipment doing things. And then, oftentimes we're intentionally, heating or cooling spaces. So we're delivering heat to spaces because we want them to be warm, or we're sucking heat out of spaces because we want them to be cool. Yeah. So one of the so we've got these different kinds of heat flow that are all important to think about when we're thinking about a solar building, or trying to make a building energy efficient. And one of the important things we need to think about is radiation, and how do we model radiation coming through windows, because especially in solar architecture, we always have lots of windows. Usually they're on the south side of a building, and those windows are designed to allow the building to get heat gain. Now we can, and this is really important, we can design overhangs on buildings to keep them shady during the parts of the year when we actually want to minimize gain. So in a building like the Lewis Center that I'm in right now, really what we want to do is we want to maximize heat gain through the windows on the south side in the winter, and we actually want to minimize heat gain through those windows in the summer. And one way that we can do that, a variety of ways we can do that. One way we can do it is by building overhangs. And if you've ever looked at the front side of the Lewis Center, you'll notice that there's a big overhang. The roof line overhangs on the south side, and that's partly designed to block, to shade. When the sun is in the summer, the sun travels through a very high arc through the sky, and so it's easy to shade in the summer because the sun is directly overhead. At least from when you're facing south, the sun tends to be directly overhead, whereas in the winter the sun is really low in the horizon, and so that overhang does not block the sun in the winter, but it does block the sun in the summer. So, overhangs are absolutely central to designing solar structures. They're key to the whole thing. But sophisticated models consider solar angles, they consider overhangs, and they consider radiation. But there's a way of sort of simplifying how we think about radiation as it arrives at our windows. And so one thing we need to think about is how much of that solar energy makes it through a window. And that we refer to as the shading coefficient. The shading coefficient is the fraction of light energy that actually reaches a window, given the fact that we may have overhangs and those sorts of things present. And then another really important term to understand is the solar heat gain coefficient. It's the fraction of light passing through a window that actually gets to us, so that there's shading, and then there's how much actually gets in. And then there's what we would call solar gain, which is how much solar energy is actually flowing into the building. So it's going to be the shading coefficient by times the solar heat gain coefficient times the amount of solar radiation that actually exists. So it's just of the solar radiation that exists, how much of it is making it through the window, getting into the space to actually be available to heat that space. And again, depending on what we're trying to do, we may use shading to alter that. We can use overhangs to alter that. We can do all sorts of things to control how much solar gain we're getting into a space. Now, so one thing that's really important in energy efficient buildings is controlling conduction exchange through windows and walls. And that is a very, very simple gradient equation that we're using in that case. So flow is going to be equal to U, which is the thermal conductivity. Again, it's just 1 over R. They're just the inverse of each other. So it's going to equal the conductivity times the cross-sectional area that that energy is traveling through. So AKA how big is the window, the roof or the wall, what size is it, times the internal temperature minus the external temperature. What is the internal temperature minus the external temperature? What is that? Help me understand this. What is that in terms of things we've thought about before? What is that? What is the internal temperature minus the external temperature?
This might be completely wrong, but is it the gradient or not?
That is the gradient, exactly. That's the driving force. The bigger that difference, the more the flow is going to be. This is exactly the same gradient equation we've looked at. Actually, this kind of strangely looks like Darcy's law, which that governs flow through a semi-porous media, because it's accounting for the area that it's flowing through. So how big is the area that it's flowing through? How much conductance is there, and what's the gradient? And that's going to be how much heat flows through that surface. It could be dependent on all of those things. How big is it? How much insulation is there, aka how much conductance is there, and what's the temperature gradient? If there's no difference in temperature between inside and outside, then it really doesn't make much difference how much insulation you have, because there's no drive, there's nothing pushing heat into or out of the space. So now radiation is actually much more complicated than conduction. Conduction is absolutely the simple gradient equation we've used before. And so I might preface even talking about radiation by saying this is going to get a little bit complicated, and then it's going to get very simple, because it's complicated, solar architects are trying to create models that are simple and can be easily used. And so they don't want them to be complicated. But I'm going to explain to you the realities of radiation, and then I'm going to tell you how solar architects actually model it, which was like a huge insight for me. I mean, I've always had sort of an interest in solar architecture, but I've also been slightly confused by it, because for one thing, I understood that the way radiation works is sort of complicated. And so that's always made me feel like, well, you have to be really sophisticated to understand solar architecture, because you're dealing with radiation, and radiation is a complicated thing to understand. And this solar architect I worked with said, no, actually, we use simplifying assumptions, and you don't need to worry about the complexity of radiation. And I'll explain how that works. But radiation flows are complex. That's what I'm saying here. Basically, how radiation flows is proportional to its temperature in Kelvin raised to the 4th power, which instantly makes it complicated. And so for that reason, we don't actually use like the same, like if you were a physicist studying radiation, you would use sort of first principles and empirical laws to model radiative heat flows. If you were studying astronomy or anything else in physics, you'd probably be using real, the real first principle equations. But that's not what solar architects do. They've created a semi-empirical parameterization that allows them to model radiation just in the same way that they model conduction of stuff. So you can see at the bottom here, to cut to the chase on that a little bit, they use a gradient equation, but you'll notice it's a little bit different from this gradient equation up here. This gradient equation considers the inside temperature, but it uses this weird looking term here called T-sol, which solar architects, I learned, refer to as Sol air temperature. It's the temperature of air on an exterior wall that produces a heat transfer rate that accurately captures the combined effects of conduction and radiation. So that's a bit of a mouthful, but it's basically a parameterization that allows them to use a simple gradient equation in their models of heat flow, so that they can design buildings that are energy efficient. So you can think of it as, it's kind of like external temperature, except it's a version of external temperature that takes into account both the actual temperature and radiation. So it's kind of got radiation and temperature parameterized together into this single term called T-sol. And it's a huge insight for me to learn that. Okay, now we get to see some kind of cool photos of like what that, I mean, some of you have been in that sunroom. It's a bit of a mess in that sunroom right now. We're not doing a great job of keeping it neat. We do use it to grow plants and starts, but it's actually way cooler than it looks if you walk in there. And this is a design that a group of Oberlin students were involved in developing. We looked around for ways to do passive solar architecture in that building next door, and they sort of found this design, which we used in that sunroom. And actually, I've used this same design in a sunroom I built on my house because I thought it was such a darn cool design that I adopted it. for my house. But this is a photograph. These are photographs of what the floor of that sunroom looks like. So it's got a poured outside concrete wall, and then it's got insulation, and then it's got what amounts to this large block of thermal mass here. And if you're familiar with what a cinder block looks like, actually this, you can see my arrow here. These are cinder blocks lying down here on a pallet. And cinder blocks they're made out of concrete, but they basically are hollow concrete. They've got what amounts to tubes in them. And it just makes sense as a building material to build concrete blocks like that, because A, it's not nearly as heavy, and B, those spaces in there if you build a wall out of it, they do provide a little bit of insulation, those spaces in there. So there are a couple of reasons why it's good to have spaces in there. Less material, lighter weight, and a little bit of insulation value. But what's been done here is, imagine these blocks have those holes in them, but the holes are all lined up here. So this is basically, and these cinder blocks are cut in half on the edge here. So basically air can travel down through this, this cinder block edge, and then it can travel through all the cinder blocks here because it's going through a tube. And then you can see how these are laid down on this side, and it can come up on the other side. So basically you're creating these little channels for air to flow through underneath that floor in that sunroom there. And then, and this gets a little overly complicated here and we don't actually use it, but we put a bunch of tubes down over this cement surface. So this is after this one. We put a bunch of tubes down through here, and then we poured cement over the whole thing, but built in these little, basically little tunnel pieces so that air can flow down and go out the other side. These pieces of wood were taken out afterwards, but basically you've got this large block of concrete here, but that concrete has air tubes that go from one side to the other side in that concrete. And you might ask yourselves the question, why the heck did they do that? He's just spent like 5 minutes explaining to me how cool he thinks it is that they put these cement blocks down, they put them angled so that they get air channels in there. Why is that cool? What was the point of doing that, do you think?
Maybe as the sun moves and heats the floor, it can like the heat can travel through the cooler parts of the floor or something. I don't know.
Yes, you're exactly right. It is so that you can effectively create a much larger surface area for heat to interact, air with associated heat to interact with that floor, and thereby substantially increase the thermal mass of that floor. So to go back to a term that I introduced earlier, the diurnal heat capacity of that floor is much, much higher as a result of having this. Remember I said earlier that normally architects consider only 6 inches of whatever the material is that a wall is made of as being important to the diurnal heat capacity. Well, by putting all these air tubes down here, we've essentially made that much, much bigger than 6 inches, because we're taking advantage of all of this concrete here and the concrete underneath it as a block that can potentially store heat and release heat. This is kind of key to solar architecture, is building in big blocks of thermal mass. And this little diagram over here is just sort of, you know, giving you that idea. So we've got these different materials here: granite, concrete, limestone, builder block, adobe, sand, hardwood, softwood. All of these have different diurnal heat capacities, but as you move up in thickness, you know, once you get past 6 inches, like I said before, it really in most cases doesn't matter how much more you have. You're not going to increase the diurnal heat capacity, but by allowing air to flow down through the floor, effectively we're expanding the degree to which that material can function as thermal mass in the system. So we've like way more than doubled our thermal mass in the system by building this floor system in here. And this is a passive system. So in this system, there's no fans blowing air through here, but we could actually make it an active system pretty easily just by installing some fans to blow air down into the floor. For instance, we could have fans that were run by a thermostat, and when the sunroom is too hot, and some of you mentioned you experienced sunrooms that were too hot, we could turn those fans on and blow some of that heat down into the floor. Because the floor would be cooler than the air in the sunroom, that would cool down the air in the sunroom. And then at night, when that sunroom cooled down, we could continue those fans blowing and blow some of that now hotter floor air into the air above it. So it's a passive system, but it could be easily turned into a kind of an active system for that. Okay. So what I want to do now actually is to take, I'm going to ask you guys to open up the schedule and click on passive solar architecture, get yourself here, and what I want you to do first is to take a look at this sunroom modeling module. So I'll go ahead and open that up. So this is it's a long document, but in part it's long because in this collaboration, I sort of brought the simulation modeling skills into the partnership, and Alfredo Fernandez Gonzalez brought in the sort of expertise in solar architecture. And we wanted to design an exercise that would actually work for both of our classes. His class not being a class on simulation modeling, his class being a class on solar architecture, and my class being a class on simulation modeling. So this contains a lot of explanation about modeling that you guys don't actually need, but it contains a lot of information about solar architecture that his students might not need. But it's a module that's actually been used in a bunch of different classes across the country at this point. But this is basically the assignment is to go through here, and you can see it's got some of the same pictures in it. But what you're going to be doing is essentially building building the simple model, and I've got pictures in here which will look very familiar to you, but because his students weren't familiar with modeling, they're designed to help someone who does not have your modeling skills understand how you would build something using Stella. So this is sort of the kernel with heat flow going in and out, wall thickness, that sort of stuff. So you're gonna build a very simple solar model. And then what I would like you to do is to actually download this sunroom model here, this AS8 sunroom 200331.stmx model right now, and then open it up, and I'll say a little bit about that model. So I actually have that model open here. And are you guys still seeing my screen? Am I sharing my screen? I hope I was. I was just walking through. Were you guys seeing my screen as I was walking through the exercise? No?
We can only see the PowerPoint.
Oh, darn it. I thought you guys were looking at everything I was doing. Let me just share my whole screen. That's a confusing thing about Zoom, is you're not always looking at what other people are looking at. So what I was saying is you want to download this this sunroom modeling module, and when you open that up, oops, that's not the right one. Go back there. When you open this guy up, you will be looking at this, and this is what I thought I was walking through with you guys. So this is these are the instructions for building the model. And as I was mentioning, it has lots of little pictures of how to build things in Stella, because it was designed for his class as well as my class. And then what I was asking you to do is to download this AS8 sunroom model. And when you download that model, you guys are seeing my screen right now. You're following what I'm saying? Yes?
Yep, we can see your screen.
Okay, great. Okay, so open that model and what you're going to see is something that looks very complicated, but in fact is just it's just taking these basic concepts, which we've already talked about in this class, and which you will build in that very simple Stella model, and just kind of playing them out for a particular structure, so that this can function as a tool for actually evaluating the thermal performance of a particular sunroom. So it looks very complicated, but its basis is no more complicated than what you will build. So I'll just say a little bit about this model by way of introduction. And so one of the things that you're asked to do in this model is modify it, modify the values of various properties of it, like the thermal mass, so that you modulate air temperature within that sunroom to maintain it within, the sort of desired variability. So this air temperature stock is kind of key in that it's the thing you're trying to optimize the model for. And there are actually very few stocks in this model. There's air temperature, there's slab temperature, and then just about everything else in this model is effectively factors that control heat flow into the air, and an exchange of heat flow between the air and the slab. So thinking about the images that I was just showing you and how they relate to the model, this is the air temperature in that sunroom, and then this is that slab temperature. Showed you that kind of fancy slab material, but basically it's the primary thermal mass in that sunroom that is storing excess heat when excess solar gain is going on, and then releasing that heat back into the room to heat up the temperature of the room during other parts of the day. And the model is designed so that the air temperature can heat up as a result of solar gain. So that is sunlight coming into the sunroom and heating up that sun temperature. Internal gain to the air. So that's the flow. That's just a flow of heat based on people in the room, on other forms of heat gain, and then a gradient equation that's like whether heat is flowing into or out of that sun space to the outside of the room. So this is just heat flow between the walls and the windows and the outside. And then you've got this exchange with the slab. So this is heat flowing from the room into the slab, or heat flowing from the slab into the room. Now you'll notice these flows from the slab into the room and from the room into the slab, they don't completely connect here. And the reason they don't connect is because the thermal properties of the air and the floor are different. So one unit of heat, one unit flowing out of here does not equal one unit flowing in here, because that a change in temperature in the slab, 1 degree temperature change in the slab is going to result in much larger than 1 degree change in the air temperature, because it takes a lot more, because the cement has a much higher thermal mass than the air does. So a change in temperature in the air is not equivalent of 1 degree, is not equivalent to the change in temperature of the slab of one degree. So you have to kind of convert them from one to the other, which is part of the trick here. But again, everything in this is basically the fundamentals of it are in the simpler version of this that you'll build. And then all of this is just sort of characteristics of the walls and the windows, how much heat they allow, how much heat gain they allow in, how much insulation they have in them, etc. It's just, characteristics of the walls that make up the sunroom. And then this is, you know, the sort of exchange of heat with the slab. And then these guys are just some added kind of stocks, but they're actually just counters that count up how much heat is flowing in one direction or another, just so that you can kind of control, you know, how heat works in the system. So essentially, that's the model you're going to be working on for this. Any questions on this? All right, well, I think what I will do, if there are no questions on this. So I think too, with this particular assignment, it's going to be from here on out, I think we're basically going to be working in our modeling groups. And what I think I would like to do is to spend of the remaining time here, I think what I'd like to do is to rotate between our different modeling project groups. And I think Chandler, neither Chandler nor Max are here today. So I think I will set up 3 breakout rooms for us. And let me just escape from this and then go ahead and set up those rooms. So let's see. Are you guys seeing my screen, or am I already? I'm already out of that.
It's already gone.
Okay. Create. Let participants choose. Just name these rooms. Okay. So, okay, so don't go into the rooms yet, but you guys can now see that there are 3 rooms that you can join. Is that correct? Help me out here, guys. Yes? Okay, thumbs up on that one. Okay, I can see that.
Yeah.
So I'm going to sort of rotate through those rooms, and what we're going to do here is kind of chat a bit about where you guys are in your projects thus far. And I would like to start in the forests group. So I'm going to join that group, but I will then rotate through each of the groups and just spend a few minutes with each group, just chatting with you about your models and that, and getting started on your project. Sounds good? Okay, so why don't people go ahead and go into their groups. How are you guys doing?
Pretty good.
Good.
I'd say we're still kind of in the planning phase. You know, we just wrapped up the proposal. Now it's time to like meet up and actually start hashing out conceptualizing the model.
Wait, isn't Justin supposed to be in your group?
Yes.
Yes.
Where's Justin?
Still in the main group, maybe?
Let me see if I can move him, because maybe he's got, sometimes people have some problems. I'll be back in a second. Hey, Justin, are you having trouble? Justin?
I'm kind of hoping.
Wait, is Justin here yet or not? I thought I stuck him in here.
He is not here.
I can text him,
I'm gonna go back up.
but
I thought I just put him in here. Yeah, I'll be back. Justin, can you hear me? Just stick him in, and I don't think he's actually, I mean, he's got Zoom open, but he's not.
oh
here.
no, Justin.
Dang. Okay.
So did you try texting him, Shantanu?
I'm texting him right now.
I do want to, I mean, you guys are not responding to my emails, but I'm hoping I can get one of you to trade, because my situation is I'm skeptical that Max is going to finish this class. He's got a lot going on, and almost everyone in the class was excited about doing this this addiction model. Like, it was the one that I think is like the most popular. I don't want to have I don't want Chandler to be alone. I don't want to have a group of 3 and a group of 1. And so I'm hoping I can convince one of you to trade so that we can do that. We can make that model work. I mean, the alternate would be to have Chandler move into one of the other groups. And it seems like that's a funny thing to do when, like, actually that was probably the consensus model that more people than anyone else was excited about. Is either of you willing to switch into that group so I don't have Chandler alone on that one?
Me and Justin were kind of discussing, or sorry, all 3 of us were discussing whether we should switch. And I was thinking, yeah, originally I did really want to do opioid addiction as the modeling project. So I guess I could volunteers.
You're willing. I appreciate that, because like I say, it just feels like, I mean, it's not, it is what it is.
Yeah.
But I really appreciate that, Avi.
Sure, sure. Yeah, no problem.
And I think the nice thing about that is that I think Chandler actually has a lot of knowledge of the system. And so I think you go into it with like a background of that. So I appreciate your flexibility on that. But he's not here today. So let's go ahead and talk about your model as it stands right now, and then we can work out the details of that. So I have not reviewed your proposal, in part because I'm wanting people to give feedback, and if I start marking things up, then people aren't gonna give feedback the same way they otherwise would. So tell me a little bit about your current thinking.
Well, a place that I guess we're struggling a little was considering what would be our kind of independent variables and the things that we would focus on varying in regards to the model and I don't know, kind of sensitivity analysis stuff. Because we kind of switched it up a little from this cool idea that Shantanu had, that kind of, we wanted to make it more concise. And so we're focusing more on the process of eutrophication and how that will impact freshwater ecosystems. And I know it's something that ENVS, we've been familiar with since early on, but making a concise model out of that is proving to be a little bit more of a challenge. We're thinking that what we could vary is the rate of nutrient runoff into freshwater. So somehow a coefficient that measures like the rate at which nitrogen or phosphorus enters an ecosystem and causes the algal bloom. And then there's the question of, for a stock maybe of algae, what units do we use for that? Is it like algae per unit area, or like individuals? Like, you can't really measure that with algae, it seems. So yeah, our proposal is kind of us hashing out those ideas a bit more than having like a really concrete, like, okay, this is what we're gonna do. Yeah, I don't know. Does that sound about right, Shantanu?
Yeah. I think Avi summarized it pretty well. Kind of the issues that we were encountering when trying to think about like both positive and negative feedback loops that we could include in our model. So yeah, we were thinking of like nitrogen and phosphorus runoff,
Yes.
going into like or working with marine plant biomass, and then also like how sunlight might affect the cycles of like eutrophication of like bodies of water that we're studying.
Definitely a big shift from where you started, which I thought was forest fires. Because when you first started talking about it and saying we're not totally sure about independent variables, I was thinking, well, I mean, I guess it would be fires or no fires, but it sounds like you're in a really different space than that right now. In fact, a completely different space from that right now. So I guess what I would say on that is I want to be a little bit more tenacious about your original concept about fires and no fires, because it seemed like that was the nugget of what you were doing. And it seems like the nugget of what you're doing now is totally different. I don't think they're, well, not totally different, but to me, it seems like, trying to respect the initial idea, like, burning forests does affect nutrient runoff. And it seems like, I don't know if you tried to dig into literature on that, but that to me seems, I don't know, I wouldn't let go of that so easily to shift to something that's just much more general. There was a model a couple of years ago, by the way. Is that last time I taught this course or the time before? A model of eutrophication in Lake Erie, which is very similar to what you're talking about now. But I think you should at least give it a shot to see effect of forest fire on surrounding aquatic ecosystems. And I don't know if you guys tried to dig into the literature at all on that. Did you?
That was one of the things that led to us changing the main focus, is because we couldn't really find much literature in regards, because it's like I don't know, it seems like a very specific sort of niche subject. I don't know, there's always, well, it's interesting to say we, because now that I'm switching groups, but
yeah, well, I appreciate that. You gotta keep some ownership here.
yeah.
Yeah, but you found nothing on that, because it seems to me that someone must have effect of forest fires on. I mean, what did you use for search terms? Fire, aquatic ecosystem. Did you fire, aquatic ecosystem, nutrient? Those seem like the obvious search terms to throw into Web of Science and see what comes out the other end, because it may be. And I mentioned that this is kind of an ideal situation. If you can find a paper that describes a particular situation, and then you ask the question, can we model that situation that they're describing of like a forest fire? Because I like the idea. I mean, what you're talking about now is just, it's very, very general. I'm not saying it's a bad idea. It's been done before in the class, what you're describing now. I just feel like you had a nugget you were excited about. I want you to be tenacious with that.
Yeah, I guess it, for some reason, when we met and we were all doing this research, it wasn't very fruitful in terms of what we came up with. But in regards to literature, I think I at least me personally, I was probably being a little too specific. I was a little overwhelmed with what the subjects were, and that there's wildfires, there's also nutrient runoff, there's also like aquatic ecosystems, like what sort of chemical runoff are we paying attention to? Like, I think my search was like wildfire, mercury runoff, aquatic.
Well, let's not do toxins, because I think we can combine your two ideas here. I think if you guys narrowed your search terms down to fire, nutrients, runoff, aquatic ecosystems, maybe plankton, and narrowed it down to maybe throw the word eutrophication in there, use some combination of those terms. And let's see if you can't come up with some papers that that look at the effects of fire, because it just sort of stands and avoiding the toxics, because the toxics are going to be complicated to deal with. So I wouldn't do the mercury. I mean, unless you find a paper that's really good like on that, I would try to do something that is combining this sort of idea you've come up with now about looking at eutrophication. What's the effect of forest fires on downstream ecosystems, as a sort of like, and then, maybe the independent variable is just, different degrees of fire intensity or fire presence or absence, and how that's going to affect downstream ecosystems. And let's just at least see. I'm not saying, if that doesn't work out, we can move in another direction. I just want you to push a little bit harder on your initial concept, because I think it was interesting, and that's what you guys were initially excited about. I just want to see if we can't find that. Jonathan, you're nodding your head yes. You're with me on this, aren't you?
Yeah, no, I'm just agreeing. I'm writing notes of what search
Try
terms we
those as
can.
search terms, and you want to use forest, you like forest fire, put that in parentheses, because then it'll do the whole forest fire. And I'm talking about your search strategy here, like what you will actually type into an advanced search in Web of Science. Forest fire, and put those in parentheses, so the forest fire is one term, and nutrients, and aquatic, and see what you get on that. But the other terms you can throw into a mix of various combinations of terms are eutrophication, to see if you have something about forest fire and eutrophication, which I think that's kind of where you want to be, is in the forest fire / eutrophication. It could be you just type in forest fire and eutrophication and see what that does for you. But you might want to put in there, these other terms I suggested, like plankton, and let's just see if we can't find something. And I can help you if you need help on it. Just tell me what you're finding when you do that search, and what you're not finding, and what you're using for search terms, and then and tell me if you're getting stuck, and I can do some searching if you're getting stuck, and see if I can do any better than you are. But I want you to try a little bit harder, because I think I have a sense. I haven't done this search, so I don't know, but I have this sense there's got to be something interesting out there on that topic that you guys were initially interested in. Hey, Justin, you're with us. We lost you. You found us. Are you here?
Yeah, hi.
Oh, he's gone again. Anyway, I don't know where Justin came into the conversation, but yeah. Why don't I'll leave the set because I want to circle around to the other groups. So why don't you guys talk a little bit, talk more. You might even, open Web of Science together. Can you share screens? I'm not sure if you can do that while you're working together, but you could certainly on your own, but together in this group, try a little bit more searching. But I think a careful keyword search, I think that I'm feeling like there's got to be stuff out there on this that's closer to what you initially proposed. You guys good? Yes,
yeah,
go.
I was wondering, for assignment 6, should the 3 of us still work together on that, since we had started that?
Yeah, you can finish that together. You pretty
Okay.
far along with it?
Yeah.
It shouldn't,
Yeah.
the assignment itself shouldn't take that long. It's designed to be relatively simple. So yeah, just finish working on it together. Absolutely.
Okay.
Are you guys good?
Yes.
Okay. Keep me posted on how things are going, and I can help you guys out if you're having trouble. Okay. Thank you.
Thank you.
Oops, I don't want to leave the meeting here. I want to leave the room. Hey, how are you guys doing?
Hi.
Hello. All right,
So
how are
what-
you?
Good. So what are you guys actually focusing on now? I said I'd be flexible in what you guys wanted to do. What have you guys figured out you want to do?
I think we're going to focus on flood inequities in Houston after / during Hurricane Harvey, and the way that vulnerability to natural disaster, like flooding specifically, makes like it more difficult for communities to rebuild. Sorry, makes it more difficult for communities to like rebuild after disaster, and that then in turn makes them more vulnerable to future
Interesting.
disasters.
We also have like a few other elements that were observed specifically that like have been observed like in several instances of like flooding inequities, but like in Houston also like the FEMA budget distribution and like the like whether or not people have flood insurance, and then like also kind of just like land use in like lower income versus higher income neighborhoods, and like how being close to like hazardous facilities has impacted like rebuilding since floods have happened.
So it sounds to me, just hearing what you guys just said, that there's some question about the extent to which you want this model to be about a specific situation, or whether you want it to be more generally about sort of hazards.
Well, I think I think we're using Houston like as a case study to model this, just so that like we can get data from somewhere, right? Like actual, because it like a lot of it is like softer variable stuff, I guess. Like it's more of like it's harder to find that if we're not looking at a specific area. And I guess also I was wondering about like if we were looking at like geographic distribution of like FEMA social vulnerability indices and stuff like that. If that's because there's kind of like a lot of like maps and stuff that show the distribution of that. Like, is it possible to kind of do like some sort of like spatial stuff in Stella more? I mean, talking about like the passive solar and sunroom stuff, it does sound kind of like there is some possibility for that, but I guess you weren't sure because it's like we wanted to focus on this specific time frame in order to, or like specific event in order to like get good data for it. But at the same time, like Stella is very based on time, like it models things over the course of time. And so I guess that was also a question of like how we can reconcile those things.
I think, yeah, what Ari said about using this as a case study is true to an extent, but kind of like the findings of like how like inequity played out and like the cleaning up and like the rebuilding of floods is applicable in many natural disaster instances. Like you can look at like the wake of Katrina in New Orleans, or like many other sites where this like inequity has shaped kind of how the city was rebuilt since then.
Right. Okay. I think you guys have the kernel of a fantastic model here. Here's my suggestion. In terms of like specificity versus generality, which is I think what we're kind of dancing around here a little bit, is I like the idea of framing this around either a particular situation or a set of situations. So like Houston being one of them, it sounds, Mavs, like you have some other thoughts about other situations, but then actually building a pretty general model. And not like my experience in 20 years of teaching the course is it's very rare. It's very rare for students to get to the point where they're calibrating the model because there's just not enough time. That takes a long time to pull that off. So I think you're just much better off thinking about, here's a specific situation, and we're trying to extract from that sort of general problems of environmental injustice, whatever the other sort of issues that are on this one, vulnerabilities of lower income communities to natural disasters. Those are kinds of the issues you want to explore. You're framing it in terms of a specific situation and saying, this situation is, we want to explore the dynamics that occur in this kind of situation, using this situation as a jumping off point. But then you're building a model that is just more general, and you're not trying to calibrate it to specific stuff. You're thinking of it more as a heuristic model that would allow someone to explore the implications of different kinds of decision-making processes, different kinds of interventions that could be made to sort of ameliorate the challenges involved. Does that make sense what I'm saying?
Yes, I didn't bring up other cities as kind of like something that I was interested in modeling, more so just to like
show the like generality, like usefulness of this model, if it were, you know, like additional question type of thing, like if it were to be adapted or if it were to be calibrated, it could use other instances and to show a larger pattern. But I don't know. Yeah, that was why I had brought that up originally.
You know, I like that idea of here's a specific situation where this is a problem, but then also, you know, this is really introductory material more than anything. Here's how this plays out in a bunch of different places where we're going to create a model that kind of lets you explore different parameters of the crisis and different parameters of the solution, the potential solution to the crisis. So as a user of the model or someone being taught a lesson by the model, it's reminding me a little bit of a very cool model that was done last year. It's peripherally related to yours, but you'll understand why, I think, once I explain it to you. They were looking at what's sometimes referred to as resource curse, like communities that have valuable mining assets, and you know, countries many times that have value, or communities as well that have valuable like natural resources and end up getting exploited. And it's useful as an analog of your situation in that they set off thinking, I think, specifically about mining communities in Appalachia, but then ended up the model they ended up created, I think, had much more generality to that in terms of exploring the dynamics of the resource curse, as they call it. You guys know what I'm talking about, that phenomenon, resource curse phenomenon. And it was a very clever and creative model because it allowed you to sort of look at a lot of different things, even though it was originally framed in terms of a particular situation. And that's where I see the similarity with what you're proposing to do. And that ended up being really quite a fruitful and interesting model. And I will share that one with you because it does have some relationship to what you're proposing to do. But I think it's a neat idea. I support it. And if you guys don't mind, I'm going to bail because I've got one more group to visit before we run out of time, but I like it.
Sounds good.
It's
Thank you.
Thank
Okay.
you.
Yeah. Sorry, I'm late arriving.
That's okay. We got 3
No
minutes. to
worries.
make most of
Getting
it.
into interesting conversations, and I also in some ways feel like, at least in my brain, and maybe you'll send me in a totally different direction, at least in my brain, I already have a pretty clear idea of what you guys are doing, but tell me what you guys think you're doing.
So basically we've got like our proposal is quite lengthy. There's like, I think there's 6 models. Yeah, 6 models. Yeah. So the initial model is gonna be the idealized model where like everything goes right in aquarium cycling. So like there's no errors on the aquarist part, and everything goes like, basically the goal is for it to look like the graph picture that we have further up. And then there's a pH crash model where the source tap water has a low KH, and so it can like sway really easily. So basically when the ammonia starts spiking, that affects the pH and the pH crashes somehow. We still have to figure that out.
Well, let me just stop you for one second.
Yeah,
Because
sure.
what I would think about this being is you've got one model in different scenarios with that model, not multiple models.
Oh, yeah.
And that one model is one in which I almost think there's like almost a gamification potential element to yours, where it's like the challenge is you as the Aquarius, and we're going to do these sort of I'm going to adjust like you'll see further on in the syllabus, there's like this choice of like special topics, and I adjust those based on what models people are doing. The analog for yours, I think there's, if you guys are familiar with Daisy World, does that ring any bells? Daisy World models. Okay, Francis.
No.
Daisy World is this sort of theoretical world composed of daisies that Watson, what the hell's his name? Why am I doing? Oh, Lovelock, James Lovelock. Actually, Watson's the guy who made the model. That's what I'm thinking about. But you know who James Lovelock is, Francis? The Gaia hypothesis. Anyway, he constructed this model called Daisy World, in which he was trying to explore how a a globe could be self-regulating. And he said, it's not difficult to create a simulation model where a globe is self-regulating. He created a world that is composed of white and black daisies. Anyway, the reason I bring it up, and we'll sort of introduce it sooner rather than later, is because he built this model, and you can go forward in the syllabus and look at the Daisy World model. And I really suggest you guys do ahead of time, because he basically created this interface where you get to play with different, you as like the controller of the world get to play with different parameters, and the world responds, you know, based on what you do. And I'm kind of thinking that might be the way you guys would want to do it, where it's basically designed to teach aquarium hobbyists how they would do this. And they get to play with various different controls to try to modulate and get the ecosystem to be stable. And you can have some preset scenarios. And in fact, that's exactly what's done in the Daisy World model. There's, you know, there are these different scenarios you can choose to run. And those scenarios will change the parameters of the model so that it runs under these different scenarios. So there's the scenarios you can run, and then you can play God and try to sort of like interact with the world. And it just seems like a very good model for your model in terms of what you might do.
Yeah.
Sorry, she's being very needy right now.
That's fine. That's what a comfort cat is for, right?
Yeah.
Yeah. No, while you were talking, she kept like clawing my leg.
Cute. Love it.
We have our own comfort cat, not in my office, but at home.
Oh,
That's cute.
yeah.
Kitty Mitty is our cat. What's your cat's name?
Her name's Dorothy.
Dorothy. Yeah. My son named Kitty Mitty when he was 4. So
Oh,
that's
wow. That's cute.
This is Dorothy.
Dorothy. Hey, you guys might not be able to work in the same space, though, I'm realizing, because of your
Yeah, I got
comfort
a
animals
bird and
may
a
not in
cat.
fact be compatible with each other.
That might be a little bit of a scuffle.
Maybe. I don't know. She
I'm worried about who might win in that situation.
Yeah.
I feel like Sweetie would win. She's very
Really full of rage.
Sweetie would win.
Really?
So much anger.
Dorothy would sooner hide than chase. She like does not chase.
Yeah.
Right.
But yeah, I feel like we have a good handle
Yeah.
on what we want to accomplish.
Yeah. Do take a look at, I really suggest you take a look, go ahead a little bit in the syllabus and open up the Daisy World model, because I think it is, we haven't talked about interfaces yet in the class. We just haven't, you know, it wasn't important to do that, but you can develop modeling interfaces that are designed for people who know nothing about Stella, so that they basically have like a simulator and they can play around with dials and knobs, and it'll behave differently depending on what they do. And I'm thinking, I mean, I'm not trying to project too much onto you, but it seems like that might be where you'd want to go with this.
Yeah, that sounds like an interesting idea, because then like it's really interactive. It's not just them.
Exactly.
being
It's
out of
not just
bubble,
like,
not
here's
just-
what happens. It's like you get to play
Right.
with it. It's
Right.
sort of like, and you can make decisions. And here's the implications of those decisions. And
Yeah,
yeah.
that would be really cool.
Okay. All right. I gotta let you guys go.
Okay.
We're past. Okay.
All right. Thank
Sounds
you.
good, guys. Take care.
Bye.
Bye.